Yeah, so first of all, well, no, first thing which is important is that what I'm going to talk about today, so it's really a teamwork. And so I want to acknowledge Emiliano Renzi, a former postdoc of mine in Loughborough University, who was involved, Claire Bergin, PhD student, Tatiana Kusina, PhD students, and Daniel Santiago, PhD students, and Daniel Giles, a former PhD student now at UCL. And but let me start, of course, with wishing you a happy birthday, Jean-Marc. And so I will spend a few minutes, to say a few things. So first of all, I went back to my CV and counted the number of joint papers we have, and I found 23. So between the years of the first one was in 1988, and so that was a joint paper with Joe Keller, actually, and that's I was a postdoc at the Woodsole Oceanographic Institution, and I met Joe Keller, and he gave me a problem to work on, weir flow, and of course, Jean-Marc was involved. Then the second one I put here, that's 1989. And actually, this one is interesting because, so I did my PhD in civil engineering at the University of Wisconsin in Madison. So that's where I met Jean-Marc, and I started with a master's, and then I stayed for a PhD. And my PhD supervisor in civil engineering told me, well, let's see, for your PhD, what would you like to do? And well, let's talk to Jean-Marc Vanenbroek. He's in mathematics. And he works on free surface flows and so on. So let's talk to him. And Jean-Marc came back and suggested something on sluice gates, but for some reason my PhD supervisor was not that interested. So then I did something else. But then I stayed in touch with Jean-Marc, and then after that I moved to Worcester Polytechnic Institute, and the first summer there, I went back to Wisconsin. Jean-Marc had some money and invited me, and that's when we worked on this flow past the triangle. And then so that was the summer of '88, and then we submitted the paper right after the summer, at the end of the summer. And then the other paper I want to mention, and that's it after that. So it's two reasons to mention it. The first one is that it's probably one of the most cited papers that we had together, and it all started at a conference in Florida. So Brooke Benjamin was giving a series of lectures, and Mark Groves probably remember that conference quite well. And then with Jean-Marc, there had been a paper by Longe Higgins that had come out in '89, and he was looking at these capillary gravity solitary waves in infinite depth, and then he was computing one part of a family of solutions. And then with Jean-Marc, I remember we went to the library and we started to look at some papers, and then we came up with an idea of where these waves were coming from. And actually, there is a bifurcation there at the minimum of the dispersion relation. And so then we wrote this paper. But the first one we had, actually, there is a forcing on the free surface. So there is a pressure disturbance on the free surface. And so that's the other reason why I put this paper, is that the link with what I'm going to talk about, Meteotsunamis. So it's a pressure disturbance on the free surface, and then the tsunami that is generated. So that was for the yes, and actually, well, yeah, it was another reference to your work will come later. So, okay, so tsunamis. So usually, well, when we study tsunamis, there are three steps: the tsunami generation, the tsunami propagation, and then the tsunami runup. And so here are some examples, some illustrations. the Indian Ocean tsunami, and then the Japan tsunami in 2011. And but you know, the majority of tsunamis are either generated by earthquakes, underwater earthquakes, or underwater landslides, or also aerial landslides. But so these are the main. But you know, this is really the primary source of tsunamis. And but you know, there are also some examples with landslides. So then this is well known, because a lot of people have worked on this, and especially since we had the 2004 tsunami, the 2011 tsunami, so more and more people worked on this type of tsunamis. So here is just a summary of the you know, what happens with this at the fault, and so then there is this motion, and then essentially it pushes the water up, and then and this part goes down, and then it creates the wave, and then it propagates. And a bit similar with the underwater landslide. So this thing starts to go down, and then the water goes down, and then of course, you know, it goes back up, and then the wave is generated, and then it's the tsunami starts in both directions. So then for this type of tsunamis, I'm talking now about the tsunamis generated by underwater earthquakes, then mathematically speaking, what we do is, so first of all, we compute a deformation of the sea bottom. So, and that's there are some analytical solutions for this. One is the Okada solution, which, by the way, you know, it's an analytical solution, but it's a relatively complex. So in the literature, you know, there are a lot of typos in the various papers. But and then essentially, you know, the simplest way is that this deformation, then it's translated, it occurs instantaneously on the water surface. And so the water surface that was flat before the earthquake is suddenly deformed, takes the same shape as the deformed sea bottom. And that's because if we assume that the water is incompressible. So then, yeah, so this Okada solution is based on dislocation theory and fundamental solution for an elastic half space. And then you can start dividing, you know, into several sub areas. So then you can add some dynamics to it. So there are several levels of complexity that can be added. This is an illustration for an event in Java in 2006. And here we call it passive because it's simply, there is this deformation of the sea bottom translated to the surface. Okay, so that's the classical tsunamis. Then there is another type of tsunamis, the Meteotsunamis. So they are meteorologically induced. So then, you know, once they are created, you know, they are like tsunamis in terms of the periods and the wavelengths. So they are generated by mesoscale atmospheric perturbations traveling offshore, such as squalls, gravitational waves, hurricanes, and weather fronts. So, and then as the waves move toward the shore, they are amplified by various types of resonant mechanisms that can drive their amplitude up to several meters. So what are these resonant mechanisms? The classical one for meteotsunamis is the Prudman resonance. And so it's traveling pressure perturbation that pumps energy into a wave moving from deeper to shallow water with the same trajectory and speed. So you have the atmospheric perturbation, and if you have the wave, you know, traveling, then if the Froude number based on the speed of the atmospheric perturbation divided by the square root of GH is of the order 1, then you can have a resonant phenomenon. So, and then in the literature, you read that if this Froude number is between 0.9 and 1.1, then external resonance is possible. you will see later that in our case, it was closer to 0.6 or 7, our Froude number, and still, we got some amplification. Then the second way is shelf amplification. So where tsunami traveling towards the shore increases in amplitude due to the decrease in water depth. That's relatively classical. Then the basin and or harbor resonance, same thing for classical tsunamis. So when the tsunami frequency is close to the resonant frequency of the basin or harbor that it's traveling through. And then another one, the Greenspan resonance. Now it's the speed of the pressure perturbation traveling along the coast is close to the resonance speed of longshore edge waves. So all these, but this is definitely the most common one. The first one people check when there is a. So in Europe, there are essentially two groups that have been working on meteotsunamis. So one is based in Croatia, and one is based in Spain, in Mallorca. So, and probably, there are groups there because they have experienced meteotsunamis. So here it's taken from a paper mixing. And then there is Rabinovich in Canada, who has been working a lot on meteotsunamis. But so this was the hotspots for meteotsunamis in 1995, and then now in 2015. So the number of hotspots is increasing on a regular basis. So actually you see that before there was nothing, in the UK, then in 2015, the UK was added. And so probably in the next version, Ireland will be added as well, and France also. So there are not that many illustrations. It's not as dramatic as some of the classical tsunamis, but here's one meteotsunami in the Netherlands, and then there was some modeling that was performed for that. There is a YouTube video. Maybe I will not. It was online, but then internet stopped, so I don't know. I don't want to risk it. So it's a YouTube video where you see the meteotsunami come. So at this, for this particular one, quite a bit of equipment is being moved, and some people run and so on, but no, nobody was that one. But if you search on YouTube, 2017 meteotsunami in the Netherlands. Okay, so then some years back, but we had this project on the rogue waves, and then one thing we did, we looked for extreme waves in Ireland, and then and including a few in the UK as well. So we came up with this catalog, and we distinguish between storm waves, tsunamis, and rogue waves. So and most of it was based on, especially for the older events, on articles in the newspaper. So then it's interesting to see how people, describe this type of waves. So of course, there are some famous ones in terms of tsunami. The Lisbon earthquake in 1755 generated a 2-meter tsunami near Cork, and so on. So there are some examples. And so we published this paper in 2000. Well, we covered events up to 2012. It was published in 2013. And as I said yesterday, this winter of 2013-2014 was the most energetic. So then we got more extreme events. So then we published another one going all the way to 2017. So including the last 4 years or so. And so in that one, there is one, so in Ireland. And so in the first version of the paper, we put this event, we were saying that this event was reported as a probable meteotsunami. However, since then it has been reported that the 2000 event was likely caused by an underwater landslide. So you see, it's never easy to figure out what it is. In any case, we had a few meteotsunamis in that. Now, moving to the UK, it looks like, there is all of the papers related to meteotsunamis in the UK involve Williams. I don't know. I think he's in Southampton or Liverpool. I forgot. But so he's and his team have been writing a number of papers. So examination of generation mechanisms for an English Channel meteotsunami, Prodman resonance, and so on, and 8-year meteotsunami climatology across Northwest Europe. And so here it's one of the illustrations for their paper. That's for the English Channel. And then based on the type of velocities for the disturbances and the water depths, then they have this hatch area here, which is the area where the fluid number could be between 0.9 and 1.1. So, okay, so now back to, well, the main part of the talk, which is this event in 2022. So actually in the title, I put summer of 2022, because in the paper, we described 2 events, one in June, one in July. I'm not going to talk about the July one because it's not so clear. So I will focus on the 18 June 2022. And so this was on a Saturday, and I was in Cyprus on that day, and the Irish media tried to contact me. So I get the news that I didn't even know that something had happened. So then, in a few hours, you try to realize what could have happened. But I was in Cyprus. I've been, my first PhD student was Paul Christodoulides from Cyprus, and I still work with him once in a while. And here's another connection with Jean-Marc, because so Paul was my first PhD student, and the first PhD student was really in the spirit of the problems that Jean-Marc was solving. So anyway, so within a few hours, I contact several members of the group and asking, so one, I said, look for tide gauges, another one for the wind data, and then later, I asked another one to do a wavelet analysis and so on. So, and then Dan Giles at the end was the one doing the numerical simulations. But this is really tricky because, first of all, meteotsunamis in Ireland, as I said, it was not something that was known. And then the first thing the journalists want to know, what is this? So then you think, tsunami and the earthquake. That's easy to check that there was no earthquake on that day. So then landslide, you never know, but then pretty quickly, and I have a colleague in Ireland who is more, an atmospheric expert. So then he was also interviewed and said that, probably it was an atmospheric disturbance. So, and then Emiliano Renzi got some evidence in the UK as well. So on this map, so these are the locations where anomalous tidal surges were observed on that day. As I said, there was also the 19th, but I won't talk about this. And so the Solva Harbor here, so the these vortices generated here, and actually in the Japan tsunami, there were a lot of vortices like this generated as well. And there is a video for this, but and also I will show some. Well, I mean, essentially, the tide was not going the right way, so people were worried, what's going on. So, and then in Ireland, 3 locations where, people definitely saw that something unusual was going on. So yeah, so here that's the water is seen rushing into the harbor and pulling the ships there. So we'll see if the video plays. Yes.
I think the internet is on here.
No, this one is
also.
I have the file. So so that's yeah, so definitely you see the the relatively strong current, and then all the moored ships then aligning in this direction. And so that was in the morning in the day. And so now in Ireland, I don't have videos for Ireland, but these are some witnesses. So then the tide started rushing out of the harbor at around 2 p.m. when instead it was expected to come in. So, but one thing, that, initially we thought all this was, it was in the morning in Wales, but that was in the afternoon in Ireland on the same day. So, and, we think that, it came east. So then the crew of a boat reported that at around 3:15 p.m. the tide dropped 1.5 meter in 5 minutes and came in and out twice in less than half an hour. Then eyewitnesses on this bridge, the tide must have been flowing out at 6 knots, 2 hours after low water, and then 6 minutes later it was coming back. It was fast. And then in Union Hall, the tide was witnessed going in and out 5 times over the course of about 3 hours, and dropping to levels lower than have been witnessed in living memory in Glendore Harbor. So, so definitely something unusual. And so what was it? Okay, so now I'm going to show some what we call, the synoptic conditions. So at various altitudes, various types of quantities. So this first one here is the mean sea level pressure at midday. So the thing to notice here is the very low pressure here. The next one is relative humidity, and again, very high. There. Then continuing, that's the temperature and wind speed at 850 hectopascal. So definitely, we see again this these winds here, and then it's at high altitude, the map of wind speed and direction. So again, it's very strong winds. So then the next step is taking 5 weather stations across the south of Ireland. So all of these are along the south coast. And so each time there are 2 curves. So the red one is before filtering, and then the blue one is after filtering, applying a high frequency filtering. So and so it's better to look at the blue ones. So definitely, and then the shaded area here shows clearly that something happened. This and also it shows, these are put on purpose. The first one is more to the west, and this one is the most to the east. So then definitely it's traveling along the south coast. Then wavelet analysis. So that's to give some frequency time information. So here, again, that's 4 places in the south coast of Ireland. And so it's the period in that direction, and then that's the time. And then the, okay, so several observations. There is a clear pulse occurring at several locations. So you see it there, and so on. And And then, sometimes, there are two pulses, but, this is the primary peak. And then, the secondary peak. And so then the period of this primary peak is about 2 to 3 hours. So that seems to coincide with some of the observations. Okay, the next step was to try to find some correlation between the surface pressure data. So, okay, that's the slide. So earlier, so on this map, there is the correlation. So we take this one as the first one, as the base, and so then the correlation level is okay. So there are several things. The color, that means the level of correlation. So when it's dark, it's highly correlated, and then it fades. So all the others here, it means that there was essentially no correlation. So really, it was in the south. Then the numbers, that's the speed of the perturbation, and then here, that's the correlation, and then plus the offset to show that's really it's propagating in this direction. So what we got from this was an average speed of 51 meters per second for the perturbation, this angle of 43 degrees, and a wavelength of about 300 kilometers. So all this is very rough, of course, but that's the best that we could do. So here, so we say now taking the depth of the continental shelf ranging from 150 to 300 meters, we estimate that the long water wave should travel at a speed between 38 and 54 meters per second. Then what we get from this is 51. So then we thought, well, we are near the speed of the atmospheric wave. So this suggests that the Prudman resonance was the determinant mechanism that amplified the Meteotsunami. Okay, so that was all wind data. So now let's go to the water data, sea level oscillations. So then we looked at tide gauges in various locations in Ireland, one here in Wales, and then some in France and one in Spain. And by the way, this morning when I was preparing the talk, I realized that these two locations have been flipped, so probably nobody will notice, but Le Havre is there and Ouistreham. Anyway, but remember these places for later. So one in Wales, then some in Normandy here, and the one in Ireland. Okay, so the signals. So first of all, each time there are two sets of curves. So the this is the predicted tide. This is the raw signal at the tide gauge, and then this is the filtered when we detide the signal, and that's what we get. So clearly, and again, this shaded area is where we think the Meteotsunami occurred. So the most pronounced one is at Union Hall that was mentioned earlier. That's this place here with a relatively large, 1 meter change in water level. But definitely, something happened here also. If you compare before and after, here it's not as clear maybe, and Wexford, nothing. So that's interesting. Okay, so then the sea level now at Milford Haven in the UK. So here, that's the raw data, and then the filtered data, and this is really tiny. And so, no, we decided, we thought no particular anomalies, despite the fact that a Meteotsunami event was clearly observed in the area at that time. Now, there is one thing about the tide gauge data in the UK. it's that they are recorded at 15-minute intervals, not in real time like other European countries. So most basin oscillations triggered by meteotsunamis have period of 1 to 10 minutes. So then they are missed by the tide gauges. So the technology currently being used in the UK does not allow for the recording of such events. Then moving to France and Spain. So this is some places in France. That's the place in Spain, again, where we think that the meteotsunami occurred. So definitely, you know, some anomalies, again, were seen. So, okay, this is in French. That's because I remembered that this morning. So I went on, you know, on the French websites to see if I could find this event. So I will translate. So a kite surfer died on the 18th of June in this place so that's near Ouistreham, the one I mentioned earlier, after having been projected against the wall, the glass window of the restaurant during a big wind, yes, violent wind. So at about 8:30 p.m. So that, yeah, unfortunately, he passed away immediately. And this meteorological phenomenon was completely unexpected, not announced by Météo France. And it happened, you know, while a lot of people were along the coastline to enjoy the summer weather. And actually, that was the other thing. The temperature dropped. I think it was like 35 during the day, and then it dropped to 18 degrees. I mean, there was also something very strange. And here it says the wind went from 0 to more than 100 kilometers per hour in a fraction of a second. Now, this is on Twitter, so it's but you know, you get the idea. So then, yeah, almost done. Now we did the same, the time frequency analysis for the sea level oscillations, not as clear as for the atmospheric perturbation oscillations, but still, so these are the 4 places in Ireland. And again, we see, I mean, there's definitely a signal, for example, in the Union Hall. So this is a clear indication here. Then there is also some high frequency perturbations, but then at this place, it's the main signal, and then it's a super harmonic perturbation as well. So it's a bit complex, but, you know, definitely some things happen. So, and this corresponds to half an hour to 1 hour oscillations for the primary peak. So the final part, well, and here, that's the rate of change of the tidal level. So, and then at Union Hall, the increase of 1.19 meter per 5 minutes occurred at 2:45 p.m. And then the decrease, and so this corresponds well with the eyewitnesses. So just to finish, and it's going to be short because in terms of numerical simulations, you know, all these are very complex. So we did some preliminary work. And so for that, we used the nonlinear shallow water code that we developed years back. It was the thesis work of Denis Dutic, and then a postdoc, Raphaël Poncet, worked on that. And since then, this code has been used by other PhD students of my group, Stefanakis, Salmanidou, Dan Giles, and now Serge Dias at UCL has been improving the code. It has been ported onto a GPU and so on. It's a finite volume scheme. And so, okay, so now we have to deal with the initial condition. So then the surface pressure field is modeled as a sine pulse traveling from the southwest to the east coast of Ireland. The shape and the direction of travel were motivated by the pressure disturbances observed at the various stations. And so that's the expression for the pressure we impose on the free surface with some ramp here. And then for the values, so we use this velocity of 51 meter per second, this wavelength of 372, and also we have to give a period. So all this, is definitely approximate, and this is the low pressure here. And so that's the good news in terms of the atmospheric perturbation. We can say that, what our model looks quite close to the observed pressures. Okay, so now in terms of tide gauges, so that's first of all the propagation of the tsunami with the flood. So 5 minutes, 2 hours, 4 hours, 6 hours, and then that's what we get at the location of the tide gauges in Ireland. So really mixed. I mean, for example, at Union Hall, we have this first manifestation here as well, but then both in terms of frequencies, in terms of amplitude, quite off. No, this is to be expected. It's a very rough simulation, and now we would have to include the resonances into the harbors and so on that we can do if needed, but we didn't have time and we didn't have the even the bathymetry to do all this. So that's what we got. But then it was interesting. At least one thing we could do was to just play with the velocity of the perturbation to check this Prudman resonance. So here we tested 4 different velocities. The one that we picked earlier was 51, but then we see that the one that gives the highest resonance is actually the one at 31 meters per second. And then, of course, when you compute the Froude number, the water depth is not constant and so on. So you take some average Froude number. So for this one, we estimated the Froude number to be essentially 1. So that would be the one giving the highest amplification. So I'm done, and this was published a month ago in Physics of Fluids. So you can find more